Hello physics students, welcome back. We are moving into chapter 4, the addition of vectors. We continue our look at kinematics, motion, the study of motion, and we have to begin to be able to address complex motion, where there's more than one input to the same object or situation. Vectors, as you know, can address acceleration, velocity, displacement, force. All of these quantities can be represented by a vector. And we oftentimes have multiple operating at the same time. So we have to become proficient with adding them together to find out what happens. Vector addition is our method of doing that. Its purpose is to analyze vector quantity interactions and the net result of each. When more than one vector is operating, they all can add together to give you a resultant, a vector which represents the sum of that many or one vector and the effect that they produce. This is our challenge. In many cases, for the purposes of study, we begin by looking at vectors that are in orthogonal. They are in 90 degrees to each other. Then we will progress into situations where the vectors are operating at not 90-degree angles. So let's take a look at how we will address each of those situations. It is a process. We sketch the pair of vectors in a head-to-tail arrangement by drawing one of the vectors in position on a pair of coordinate axes, the tail of that vector at the origin. Then we draw a second pair of axes at the head of the first and draw the second vector on that pair of axes, tail at the origin. The vector magnitude and angle should be labeled. Determine the angle C. If angle C is 90 degrees, follow procedure A. If not, follow procedure B. Let us now look deeper at those two procedures. Procedure A is again meant for angles of 90 degrees. You would close the triangle by drawing the resultant tail to head or head to head. Use the Pythagorean theorem to find the magnitude of the resultant. As you know, that would be 1/2 of the information for the vector. Pythagorean we've seen in class and used it extensively as a squared plus b squared equals c squared. Please recall the naming convention that we have and we've passed around in our handout that addresses how to name the sides and angles in a triangle. Then we would use the tangent function to solve for the interior angle where the two tails meet. We can use tangent, opposite over adjacent from the SOHCAHTOA mnemonic that we use to recall, but we can also use sine or cosine. I will recommend tangent as it is the most efficient. We will have the two magnitudes of the sides when we begin. We will have the magnitude of the opposite and the adjacent side. The direction angle is always between the resultant and a main axis. Recall from the previous note set how we will use the conventions for naming in regard to the next closest major axis. For instance, we would have 29 degrees east of north would be one example. If this is not the case, if the angle is not a 90 degrees, we will have to call on our knowledge of angle pairs and transversal rules. In this illustration, we see that we can draw parallels between certain angles based on our knowledge of geometry. Angle 1 is equivalent to angle 4. Angle 5 is equivalent to angle 8. These are the vertical angles. Also, angle 2 and angle 3 are equivalent. Angle 6 and angle 7 are equivalent. The interior angles can also be drawn as equivalent. Angle 4 and angle 5, and angle 3 with angle 6. The supplementary rule will lead us to be able to conclude that 1 and 2, 3 and 4, 5 and 6, and 7 and 8 all add to 180. Once again, 1 and 3, 5 and 7, 2 and 4, and 6 and 8 also add to 180. This will become important when we seek to identify the first interior angle of our non-90 degree vectors. This will become procedure B, and that is what we'll look at next. Procedure B is for non-right triangle vector addition. As always, we want to stick with our plan to list our knowns and unknowns, sketch the head-to-tail arrangement, and follow the procedure as stated ahead. Procedure B. Use angle and transversal rules to determine the exact value of C, the interior angle, before drawing the resultant. As demonstrated during class, we can use our transversal rules to determine the exact value of C. Part of the information would be given in the question, and by extrapolation we can find out exactly how large that angle would be. We would then close the triangle by drawing the resultant tail to tail or head to head. Use the law of cosines to solve for the magnitude of the resultant. This takes the place of the Pythagorean theorem that we are so familiar with, and it relies upon many of the same variables. For more information on the law of cosines, see Chapter 4, Section 1. Finally, to determine the interior angle where the two tails meet, we will use the law of sines. This we will detail further in class with exercises. The direction of the angle is always between the resultant and a main axis. You can see an example on page 75 of your text. These techniques are among the most complex for our course. I highly recommend that you become proficient with both Procedure A and Procedure B. Be careful to recognize right triangles and non-right triangles and how we will assess the magnitude of the resultant vector and the angle at which the resultant meets our original vector. This will be gone over repeatedly on exercises in class to prepare us for upcoming assessments. The text in Chapter 4, Section 1 and Section 2 can provide much more detail on this and our discussions in class. As always, I'm available for follow-up, tutoring, and problem solving. Thanks for your attention, and until next time, this is Mr. K saying, stick with the physics.